at 35 here. So 2017 first class mail rates increased to 49 cents for the first ounce and 21 cents for each additional ounce. If Sabrina spent $16.45 for a total of 45 stamps of these two denominations, how many stamps of each denomination did she buy? So it's going to be set up very, very similar to what we just did. The only difference is, instead of amounts of money, we have stamps. And instead of an interest rate, we have the cost of the stamps. So we're going to look at our stamps here. So we've got stamps. And we've got the cost, or the denomination of the stamps. So Sabrina's going to go into the store, into the post office, and it says mail rates increased to 49 cents for the first ounce, 21 cents for each additional. So there's two types of stamps in the post office. There's the 49-cent stamps, right? And there is the 21-cent stamps for the additional ounce. So what do we know here? It says she spent $16.45. We'll deal with that in a moment. That's our total cost for a total of 45 stamps. So how many total stamps do we have? 45. So I'm going to put that there. Now, the total cost is like the interest. So that's going to be put down below. So that multiplies together to give you that. Do we know how many 49-cent stamps we have? No, that is unknown. Do we know how many 21-cent stamps that we have? No. If we don't know either one of them we call X, the other is the minus X. And how many total stamps do we have? So that's going to be 45 minus X. Now let's talk about the total price. And we'll call this the price. You can label them however you want. The price is going to be the stamps times the cost. So stamps times the cost is going to give me the price of each type. So the first one, we've got some stamps. Those stamps cost 49 cents. So as a decimal, that's 0.49 times the X. That's this piece right there. Is everyone okay with that? Very similar, just different wording is all. It's the same type of problem. Second part, 21-cent stamps. So that's 0.21. How many are in there? 45 minus X. And how much is the total bill? Okay, the total bill, how much do I have to pay? Total bill, 45. And I think you can finish it from there, right? Do you see how I set it up, though? That's the important part. That is where students always struggle. Not here. Anyone can solve this. Setting it up is where students make the mistakes and get confused. One more of these, then we'll look at the distance questions. Question 38. A customer at Harriet's Coffee wants to buy Italian espresso beans and Kona Deluxe beans. If he wants 4 times as much of the Kona Deluxe as the Italian espresso, how much of each can he buy for $247.50? So it's going to be done the same way that we did the other one. We have a chart so we can read out what they cost per pound. Okay, so we're going to label it again. And I think this one will finish, just so we have another example of one that we finished. So we've got some coffee beans. And so this is going to be the weight, the number of pounds. And we're going to look here at the cost per pound. And we've got two types of coffees. So we've got espresso. So I'll just label that as so EXP. We'll just call that espresso. And we've got the Kona Deluxe. So this is going to be the Kona over here. Okay, so let's see what we've got. We need to come up with our chart. So we're going to buy some espresso, and that Italian espresso is $9 a pound. So that cost is going to be $9 for the espresso. And the Kona Deluxe is $11.50. So it's a little bit of a better quality bean. So it's $11.50 there. Okay, now, when we read this, do we know how many pounds of the espresso I need? Does it tell me at all? No. So that's going to be my unknown. Now, what about the Kona Deluxe? What would go here? Does anyone have any idea? What does it say about the Kona Deluxe? Okay, so that would be 4x, wouldn't it? Right? 4 times as much. So that's 4x. And when we add them across, what do we get? 5x for the number of pounds. Okay, so let's go ahead and build our equation. Just like we did last time, the price is going to be the number of pounds of coffee times that cost. And if I look at the espresso, espresso costs $9 a pound, so that's 9x there. Then we've got the Kona Deluxe, and it's 4 times as much, so that's 4x, and it's $11.50 a pound. So that's 11.5 times that 4x there. And what is the total bill? Okay. So I'm going to go to the shop, and I'm going to spend $247.50. All right, so I need to solve this, and I'm just going to go ahead and solve it so you see another example of one that's been solved. A lot of these I don't, and I just picked this one to solve because we haven't done one in a bit, and I want to make sure we can at least do that. So I'm going to go ahead and combine these together. So I've got 9x, and then I've got 4 times that 11.50. And that's 46x. And that equals your 247.50. Adding those together, that gives you 55x equals that 247.50. We'll divide by our 55. And now, how many pounds of the espresso do I need? 2.5. Okay, we're going to divide that by 55. And we need 4.5, 4.5 pounds of espresso. We also need to find the pounds for the Kona Deluxe, because it wants to know how much of each we can buy. So what about the Kona Deluxe? Well, the Kona Deluxe is what? We look back up here, Kona Deluxe is 4x, right? So for the Kona Deluxe, it's going to be 4 times the 4.5. And what does that give me? That gives me 18 pounds of the Kona Deluxe. Now, how can I check to make sure I did it correctly? Well, how much does espresso cost? $9 a pound. So $4.50 times 9. What is that? So, sorry, 4.5 times that 9. That comes out to be $40.50. So $40.50 in espresso. What about the Kona Deluxe? We bought 18 pounds, and that's $11.50. And how much does that give me now? I'm going to multiply those together, 207. And when I add them together, what do I get for my total now? Yep, and it should come out to be $247.50. So I know I did it correctly. Is everyone okay with how I did that? I just chose to work this one out just so you'd see another example of doing the whole entire process. So we find x, we have to get both of them, and you don't have to check them like this, but I like to so you see how it makes sense. And 4.5 times that 18, 4.5 times 4 should give you that 18, which it does, right? 4 times as much. Okay, now we're going to go on and we're going to talk about distance questions. Now, for the distance questions, these can either add, subtract, or they can equal each other. And for the distance, we have to look at our direction. And we use what are called vectors. So, when they look like this, going separate directions, they add together. East to west, north and south. Okay, they're going to add together. When they overlap, they subtract. And this is like two people running a race. So when they overlap, they subtract, like this. And when they're the same, they equal each other. Where would they be the same? Well, driving to school and driving back home again. Okay? You drive to school, you drive back home. Those distances should be the same, right? It's 5 miles to school, it's 5 miles back home. Should be the same. What would these two look like? Well, these would be like trains or cars going in opposite directions towards each other. Or it can look like this as well. They can go towards each other like this. This is also addition. The only time it's going to be subtraction is when they overlap. Right? So two people running in a race and they overlap. If they overlap, they're going to subtract from each other. Now, when we build these equations and we look at our pictures, we've got to figure out if it's addition, subtraction, or if they equal each other. And then we build our equation the same way that we did the others. Some of these are actually easier than the mixture or investment questions. It's sometimes the setup, you have to draw these pictures and make sure you see what's happening. So we're going to look at question 47. And this again is on page 180. As long as you're careful, I think the setup on these is actually easier. Now, when we talk about distance, there's 3 things that are involved. When you drive a car, there's 3 things we do that we can keep track of. If we go from, let's say, your house to school, how many miles it is to school, how fast did you drive on the highway to get here, or different roads, and then also how long it took you. So rate, time, and distance. Those are our 3 components. Now, rate times time gives us the distance. That's like your interest. Multiply them together, you get the distance. So it's very similar to the interest and the pure. So we're going to look at question 47. So you go ahead and put this up here, and we'll talk through it. Now, we are going to have to draw a diagram to see what we've got. From a point on a straight road, Marcus and Chelsea ride bicycles in the same direction. Marco rides at 10 miles an hour, and Chelsea rides at 12 miles per hour. In how many hours will they be 15 miles apart? Okay, so they ride in the same direction. Okay, so from a point in a straight line on a road, they ride in the same direction. So that means they're going to be traveling in the same direction. So they're going to be going towards each other, right? Just like that. Okay, if I'm pointing a straight road, Marcos and Chelsea ride in the same direction. Wait a minute. Let me make sure I drew it wrong. Let me make sure I set this up correctly. Okay. So let's make sure we have this right here. I almost set it up wrong. From a point on the straight road, Marcus and Chelsea rode bicycles in the same direction. So make sure we have it set up right. They're going to start at the same point. They're traveling the same direction. So that means, sorry about the mix-up there, I wasn't thinking, that means that it's going to look like that, isn't it? Right? Make sure we have it set up right. I almost wasn't careful and drew it the wrong way. They're traveling in the same direction from the same point. So they're going to start here. Now, when I label these, I want to make sure I put the faster person on top. So Marco travels at 10, Chelsea travels at 12. So we'll put Chelsea on the top. And Marco down here. Okay, now each of these has a rate and a time. And I always want to put the faster person on top. That way when we subtract them, they come out correct. If you do it the other way, you'll end up with a negative answer. Why are we going to subtract them? All right, we're going to be subtracting because they do what? They overlap. So how fast is Chelsea traveling? She's traveling at 12. Do we know how long she's on the road for? Nope. Unknown amount, X. What about Marco? Marco's on the road, and he travels at what? 10. Do we know how long? Nope. So we use an X. Now we're going to look at the distance. And just like the pure, and just like the interest, distance is a multiplication of the rate, in this case, times the time. And we've got Chelsea, and we've got Marco. And we're going to look at each one, and these are going to subtract from each other. So we've got 12x from the first one, just like we did before. Okay. They are overlapping, so they subtract. Whenever they overlap, they subtract. Marco is 10x. And what's my total distance? Total distance is going to be 15. And we can solve it out. This one's simple. Put them together, and we get 2x equals 15. Divide by the 2, and we simply get x is, and you can either write it as 7.5 or 7.5 hours. And you could even write that if you wanted as 7 hours, 30 minutes. Either way. And that's going to be your time. Right? Simple enough to do. So it took them 7.5 hours. Now, why are we subtracting? Here's the important part. Why are we subtracting? Because they are what? Overlapping. If they overlap, they subtract. Question 49 is the opposite. So question 49, and they make tables. I don't like tables. I think the pictures are just easier to understand. So we're not even going to go look at the table because pictures are easier. So we're just going to use the picture they've got here. So Atlanta and Cincinnati are 440 miles apart. John leaves Cincinnati, traveling towards Atlanta at an average of 60. Pat leaves Atlanta at the same time, traveling to Cincinnati in her antique automobile. She averages 28 miles an hour. How long will it take them to meet? So they're going to meet somewhere here. When we look at this, are these overlapping at all? No, right? One's going east, one's going west. They're going to meet somewhere. So this would be an example of addition. I'm going to try to pick one example of each type. This one I'm not going to solve out. All right, we just solved one a moment ago. This one we're just going to build the equation. So we've got John and we've got Pat. And they're traveling towards each other. And they're going to meet somewhere here. So they're going to meet right here. This is going to be addition because they don't overlap. Right? They're going towards each other. What about John? What's his rate of speed? John's going to go at 60 miles an hour. And what about Pat's rate of speed? She can't go as fast. She's going at 28. And how long is John on the road for? Don't know, so we use an X. What about Pat? Don't know, but that's also an X because they leave at the same what? Time. Now let's build our equation. What's my total distance, by the way? Just so we have it, 440. It's 440, isn't it? Yep, so 440, that's going to be my total distance. So now we can build our equation. Okay, rate times time. Let's look at John first. And John is 60x, right? Those get multiplied together. Is everyone okay with that so far? We're going to add Pat to that. And that would be 28x for Pat. And what is the total distance? Total distance in this case is going to be what? 440, right? Okay, can you finish it from here? Should be able to pretty easily. Is everyone okay with how I set it up? That's the part that students always struggle with. Next week, we're going to start preparing for our exam. And next week, we're going to break up into groups, and I'm going to give you problems, and you're going to work together on them and make sure you know how to solve them. So that's going to be next week. We're going to do more of these. But you're going to have to do them on your own next week. Question 53. Well, let's not do 53. Let's.
So after we find the answer,
Sure.
Would it be?
Okay. When you find x, what is x? Yep. And what does that mean? Okay. You found that answer to be 5 hours, right? X is 5. X was what? The time. So that's how long they're both on the road for. And that's what they want. So he's going to be traveling for 5 hours. She's going to be traveling for 5 hours, and they're going to meet at some rest stop here. But if he leaves and she leaves at the same time, so if they both leave at 8 o'clock in the morning, okay, they're going to meet it in 5 hours. That's what that means. So x in this case is the time. And you solved it and you got the 5. That one was easy to solve, but that x is the time, so it would be 5 hours. So in 5 hours, they're going to meet at some rest stop. Okay, let me look at one where they're equaling each other. Let's look at one. And let's see. Let me find one where they equal each other here. I know there's one that we can do where they equal, or I can make one up if we can't find one. I'll just make one up. So I'm just going to make one up that's going to be an equals. So John travels to an appointment in the morning and averages let's say 60 miles an hour. Later in the afternoon, he averages 50 miles an hour. The morning takes, let's say, let's make sure I've got this right here. So let's say the morning takes 3 hours to travel to his appointment. How long will it take in the afternoon to drive back? Okay, so this one's going to be kind of similar to the others. Now, I said I wanted to pick one that's equals, and I couldn't find one in the textbook. I know there's some in here, but I'm just going to go ahead and make up this one. So this one's going to be equals because he's going to an appointment in the morning, and he's going to average 60 miles an hour. Later in the afternoon, he averages 50 miles an hour when he comes back. So there's traffic, so it slows him down. In the morning, it takes, and I didn't put it in here, 3 hours, should have wrote that down. 3 hours to his appointment. To get to his appointment, it takes him 3 hours. How long will it take him to drive back? So let's see what we've got. Now, what do we know here? These are going to equal, right? Because if I drive to that appointment, and let's say it's 100 miles away, say I have to go to the doctor, it's in a different city. So let's say it's in Wichita or something. I have to drive that 3 hours to get there, okay, on the highway. They're going to equal that distance because it's the same amount of miles to there and back. You're doing the same route. So we're going to go faster in the morning because there's less traffic. And let's see what we got in the morning. So in the morning, how fast are we going? Right? In the morning, we are traveling at a rate of 60. Do we know how long it takes us to get there? We do. Yeah, because in the morning, it takes him what? 3 hours. Now, we don't know how long it takes him in the afternoon. But in the afternoon, what do we know about that? Okay, we're going slower because there's traffic. So maybe you can't go as fast on the highway. So the rate in the afternoon is going to be 50. Do we know the time that it takes in the afternoon? No, so it's going to be X. And this may not come out to be a nice whole number, and that's okay. Right, we're going to get that time. And it should be more because we're going slower. So what does your equation now look like? Well, we're going to be working with the distances, and they're going to be the same. Because we're looking at the distance, and how do I find the distance again? Rate times the time. And in the morning, we're traveling at a rate of 60, and it takes me 3 hours to get there. In the afternoon, we're traveling at 50, but I don't know how long it takes, so that's going to be X there. And we can finish it, because 60 times 3, well, that's 180. And we'll divide by our 50. And that's not going to come out to be a nice whole number, but we can go ahead and get the decimal equivalent or the fraction. And it comes out to be 3.6 hours. So it takes a little bit longer. Is everyone okay with how I did that one? Now, why are these going to be equal? And I wanted to make sure I did one that's equal, because I know in intermediate, you'll see ones that are equal once in a while. And why are these equal? They are equal because we're going somewhere, and we are what? Coming back. And in the morning, you're going to go a little bit faster because maybe there's less traffic. In the afternoon, after your doctor's appointment, maybe there's more traffic, so you're slow to 50. It takes 3 hours in the morning to get to that appointment. We need to figure out how long it takes us to get back. So that's going to be unknown. That's x. And we've got 3.6 hours in the afternoon. Let's go ahead now and find the distance. How far is it to the appointment? Let's try to figure that out as well. How many miles is it to that appointment? Okay, if I ask you that part, does anyone know how far it would be to the appointment? Okay, think about what we've got. We've got rate and we've got a time, don't we? Okay, and some questions ask you this. So how many miles is it to this appointment? Yep. And how did we come up with that? We took the 60 times the what? 3, right? And 60 times that 3 comes out to be 180 miles. So it's 180 miles to that appointment. It's going to be the same if we did it in the afternoon, right? They should be the same. Because in the afternoon, if I take my 50 and I multiply that by the 3.6, I also get the same what? 180 miles. It's just we're traveling slower. And some questions may ask for the distance. How do you find the distance? That's the rate times the what? Time. Okay, so it's 180 miles to that appointment, and it's going to take us 3.6 hours in the afternoon to get there. 3 hours in the morning because we're able to drive faster. But it's 180 miles to that appointment. Okay, let's look at another one. How about, bless you, how about question 56? Let's try to see how we would set up 56. Bless you. 2 cars leave towns 230 kilometers apart at the same time, and they're going to travel towards each other. One car travels 15 kilometers slower than the other car, and they pass each other in 2 hours. What are their rates of speed? Very similar here. We've got different pieces that we know, though. So first off, they are 230 kilometers apart and travel towards each other. So if I look at this from a picture, what does it look like? It looks like this, doesn't it? Okay, 2 cars are going towards each other. So what would this one be again? Addition. We have 2 cars and 2 different rates of speed. And I'll call this one car 1 and this one car 2. So the first car, we know nothing about. Okay, it doesn't tell us how fast the first car is going. So rate of speed is unknown. Now we do know that they pass each other in 2 hours. So that means my time for both of these is going to be what? 2 hours for both of them. Times are the same. So the first car, we don't know how fast they're going. So that's the unknown part. What about the second car? Do we know how fast it's going? No, we don't. But we do know that it's traveling what? 15 kilometers slower. So that's going to be x minus what? 15, because they're traveling slower. Now let's look at our distance. Distance, again, is the rate of speed times the time. And we're going to add these together. So car number 1, rate times time, that's a 2x. Car number 2, what would it be? 2 times x minus 15. And what are they going to equal when we add them together? Can anyone tell me what's going to go here? Okay, let's look and make sure. Yep, it looks like they're 230 kilometers apart. So you're correct. So the 230 is going to go here because that is the total distance apart. Okay, and you can finish it from there, right? But do you see how I set that one up? This one again is addition. Why? Because they're going towards each other. Okay, let's try it. Another type of question here. How about, these are all very similar again, they're a little bit different. How about 58? This is a percentage type of question. So this one is a little bit different. Okay, this is a percentage question. And we need to make sure we know how to deal with these percentage questions. Paula received a paycheck for $585 for her weekly wages, less a 10% deduction. How much was she paid before the deduction? So think about if you get paid. A lot of things come out, right? Taxes, insurance, whatever deductions you might have. Okay, so how much would I actually have had before my deductions? This one is a little bit different. Percentage questions, though, we have to make sure we understand how they're set up. Percentages have to be linked to something else, so they have to be linked by multiplication. So let's talk about how we would set this up. So the total amount of money that I make is going to be the paycheck, right, that I get paid. Well, let me set it up right so it looks right. Okay, make sure I set this up so it makes sense here. The paycheck, okay, this is what my paycheck is going to be. My paycheck is going to be the total amount minus the total times the percentage of deductions. Okay, this is the deductions here. Yep, and I'll move it so we can see it here once I've got it all set up right. Okay, so this is what we've got. Okay, if we think about what our paycheck is, right, you get a paycheck. Your paycheck is going to be that gross pay that you get minus all your deductions. Is everyone okay with that? That's how it works, right? We get a paycheck. How many hours we worked is not what we get paid because we have these deductions for taxes, for insurance, things like that. So this is how we're going to set it up. This is a percentage of the total. So how much did we make in our paycheck? If we look at question 58, we made $585. That's what our paycheck was. Do we know how much we really made? No. So that's going to be X. Now, what about our deductions? How do these deductions work? What is my deduction percentage rate? 10%. And how does that work? That is 10% of what your total is. So let's take a real easy example so this makes sense. Let's say I worked and I was supposed to get $500. Okay, this is another example. I just want you to see with numbers how everything relates. So I work and I put in my hours and I'm supposed to get $500. Now the government gets 10%. How much would I really get? Okay, I take my $500 and I take 10% of that $500. That's $50. That's my deductions. So then I take my $500 and I take out that $50, which is my deductions, right? And I get $450. How did I come up with that $50 deduction? I took the total that I made and I took it times the 10%, right? So that's why this is the total times the percentage. Does that make sense now? Because I always try to relate things back to something you understand. We understand how paychecks work and taxes work. So we don't know what our total amount was. So that's going to be X. What about my deductions? Okay, what deduction rate do I have in this case? 10% deductions. So that's 0.1. And we don't know our total, so we have to put the X there. Why do we have to take that 10% times the total? Because you can't leave a percentage by itself. Percentages have to be multiplied by something else. And the more money we make, the more the government gets in taxes. Now we can finish this. So let's go ahead and finish it out. And this is easy. Watch your decimals. This X, that's a 1X. And 1 minus 0.1, that's 0.9X. And that equals your 585. Okay. Divide by your 0.9. And what do we get X to now become? Okay, 585 divided by 0.9, we get 650. So that's how much I really made, but I only really saw 585, right? So I made 650, but I really only got 585. How can you check your answer? Well, if I take and subtract these, I should get my deductions. So let's see what my deductions are going to be. If I've got $650, 10% deduction, that's what? $65, right? That's how much the government got in taxes. 650 minus 585, what is that? $65, right? So it makes sense. Now again, you don't have to check these. The only reason I'm checking them is so you see how it goes together. If I just draw up equations, it doesn't make sense and you won't understand how I built them. So a lot of this is just trying to relate back to something that you understand so you can see how these actually came about. Because if I just build them for you, you'll never understand it. I have to come up with examples of things that we understand. Let's do one that's similar again. 62. Another percentage type of question. We'll do one more. We'll take a break after this one. So we'll do this one and then we'll take a break. Ricardo paid $7,000 for a used car. This included a 10% sales tax, less a trade-in allowance of $1,250 for his old car. Find the actual price of the car he purchased. So, Ricardo paid $7,000 for this used car. Now, this included a 10% sales tax, less a trade-in allowance of $1,250 for his old car. We want to find out how much this car actually cost. So how are we going to figure this out? Well, let's talk first about what we paid. Okay, so the price paid. The price that we paid is going to be the actual cost of the car. Okay. Then we have to add on the sales tax. This is the sales tax here. So this is going to be our sales tax. And then what else do we have here? We also have, we also got $1,250 for credit for his old car. Okay, so we've got, this included 10% tax, less a trade-in allowance of $1,250 for his old car. We want to find the actual price of the car that he purchased. Okay, so this is what we've got. Now, let's make sure we understand what's happening when we talk about the cost of the car. When we talk about the cost of this car, we've got the car. Now, let me make sure I set this up so it makes more sense here. I want to make sure I set it up correctly. Okay. Because we've got, let me just double check to make sure I've got it set up correctly. So I want to make sure we deal with this extra price in here correctly. I just want to double check things before I make a mistake. Okay, so we need to make sure we've got this set up correctly. So let's make sure we set it up correctly. We want to make sure it all makes sense to us. So the price paid is going to be the cost of the car. Okay, so that, $15,000, whatever we paid for this car. Then we take off what? Then we take off our trade-in. Okay, so the cost of the car minus the trade-in, and then we have to take the sales tax on that. Because that's how it works, right? If you remember how a dealership works, a lot of times you're better off trading in a car to the dealership because you get to take that trade-in cost off in your taxes. Okay, so how much did we actually pay for this car? Okay, the price that we paid for this car was $7,000. Now, do we know the cost of the actual car itself? No. We got to, though, take off some money in the trade-in. And how much money did we get to take off in the trade-in? We traded in another car, okay, and this car that we traded in was $1,250. So we're going to take off that $1,250 there. Now, what about the taxes? We don't pay taxes on the cost of the total car because you get to take off the trade-in value, right? That's how dealerships work. They pay taxes on after the trade-in. So what about over here? This is the taxes. And for the taxes, we paid 10%. Wasn't it 10%? Yep, 10% sales tax. So that's 0.1. That's your tax rate. And what are we taxed on? X minus what? $1,250. Because that's how it works. If you go to a dealership, okay, a lot of times you're better off to sell the car to the dealership because they can take that trade-in value off in the taxes. Because that's how they do it. Before they do the taxes, they have to take the value out. Let's go ahead and see if we can't figure out now what we really paid for this car. What the cost of the car actually was. Okay, so we got the price that we paid, so let's go ahead and work this out. So we've got X minus $1,250. We're going to go ahead and distribute the 0.1 through. And that's going to be 0.1x minus, we've got $1,250 times that 0.1, and that's $125. That's the taxes on the used car, okay, because we got to take that out. Combine everything together. 1x here. Make sure you're careful with the decimals. So when we put those together, we're going to add them together, right? Because you got to pay. You got to pay your taxes. So adding those together, we get now 1.1x. And how much in deductions? Now we've got the $1,250. And we're going to add to that $125 off as well. So that's $1,375. And that is your $7,000. We're going to go ahead now and add that $1,375 to each side. Let's finish this out and see what the car really cost. So we've got our $7,000. We're going to add to that $1,375. And that gives you $8,375. And that equals 1.1x. We'll divide by our 1.1. And that gives us now x equaling. It looks like 7,000. And we're going to round here, $614. Okay, and that's what you would pay for the car. If you were to buy cash for that car, that's what it would be. But see, that $125, that's the money you'd actually save by taking it in and trading it at the dealership, because that's how dealerships work. If you trade a car in at the dealership and they give you money for it, you get to take that off in the taxes. So sometimes, again, it might be beneficial, depending upon what the dealership gives you and how they work out the deal, to trade it in rather than sell it yourself. Because if you sell it yourself, you're going to have to pay that in taxes. If you sold it yourself, you'd have to pay that $125 back in taxes. Because the dealership can take it off, but you can't. So that's, again, why sometimes selling a car to the dealership is not necessarily a bad thing, depending upon how the deal's worked out. So let's take a short break, and let's meet back here at 10:20.